All right, so we just kind of described the whole concept of resolution for a chromatogram. And we said that resolution is something that we don't want to be subjective. And we need an equation in order to calculate resolution. And I want a number that's greater than 1.5. If I get a value that's greater than 1.5, then that means the two peaks are resolute, they are separated enough, and I could feel okay with the data that's coming from it. So to calculate resolution, I'm basically going to take T sub R of B. So that's the retention time for one component, and then I'm going to subtract that from T sub R A, which is the retention time of the second component, and I'm going to take that difference and I'm going to multiply by 2. And then on the bottom, we're going to take the width of A and the width of B, and we're going to add these two things together. All right, so when it concerns resolution, what do all these variables represent? Well, let's say that we get a chromatogram and we get one component and we get two components. And I'm going to call this A and I'm going to call this B. That's kind of the order that they come off in, so I go alphabetically. A first, B second. All right, so if you look at the top, it's going to tell you to take the retention time of B and subtract that from A first. So the reason that they tell you to do that in the equation is because B always comes out second, and this will always have the larger retention time. And because that has the larger retention time, when you plug it into this equation, you'll get a positive number. So that's why it's kind of structured that way. You just want to make sure you get a positive value there when you do the subtraction, and then you multiply it by 2. As far as the W's go, the W's are going to represent the width, and the width of A and the width of B. So those widths are basically the widths at the base. So how far or fat is that peak in the chromatogram? And the same thing happens with B. And what they do is that they will measure these in form of time, not actual centimeters or millimeters. The widths are going to be measured in form of seconds or minutes most of the time. It really depends on the reporting, and it depends on the chromatogram itself. So seconds or minutes will be the width. And of course, the retention time here, those also will have a matching unit. That will be in time as well, either in seconds or in minutes. And that really is just up to the chromatograph and the chromatographer to report that value, so that way you can use them a little bit later down the road. So the nice thing about these is that everything's got to be given to you. You just got to be able to plug them into the equation and solve for R. So the retention times are going to be given. The width at the base is going to be given. There's going to be no issues there. Just make sure they're the same unit of time when you plug them into the equation, and you'll be okay if that begins to happen. So here's a diagram of what we're talking about when it concerns resolution. And if you look at the first one, we automatically know there's no way those two peaks are resolute. They're not separated. We need them separated a little bit more. It's just one big old fat blob that comes off at one time. And who needs that? I don't need those fat blobs. I need something that's going to be a little bit cleaner. So we go to B, and B's another example of two components that are separated. And some people might look at this and say, you know, those peaks are separated because I see two humps, right? And it looks like the middle, the valley, goes down to the baseline. So why aren't these two peaks separated? And then other people would come in and they would say, no, those peaks are not separated. Are you crazy? There's still more work to be done in order to make sure that these two things are separate from each other. So then we go to C, and C I think no one would argue with, and C would basically say these two peaks are separated, there's no questions about it. This is a very clean peak that goes straight up, straight down, and clearly it goes to baseline. And then the second peak goes straight up, straight down, and clearly that goes to baseline. So I think that C everyone would agree that those two peaks are separated. And for A, I think everyone would agree that those two peaks are not separated. Where we find the problem is B. And this is an issue that we've struggled with for years and years and years on how to determine if something is fully separated or not, and not really just be subjective about it. So that's why we've introduced this resolution equation. By plugging in the values in the resolution equation, we will be able to go through a series of mathematical steps to basically prove that these two peaks are either well resolute or need improvement, and they need separation a little bit more. So that's why we've incorporated the equation. That's why we use the equation, and we just kind of make sure that the peaks are going to be separated before we start processing it with values and numbers. Now, we've talked about how to increase resolution in the past video, and the very last one that you've noticed with me listing was this thing called the lengthening the column. Make the column bigger, right? So if we increase the column length, then we should be able to increase resolution. And that's true. However, I told you that time is money, and that sometimes we just don't want to go through the time involved in letting these things react and separate in the column and having these hour-long run times that we might need in order for our chromatograph to be processed, right? Okay, well, there's going to be some other issues here with choosing column length and making it longer. And again, this is one of the reasons that we try to stay away from this until we absolutely have to. So if you increase the column length, you're actually increasing the number of theoretical plates, right? You're putting more stationary phase on the inside. That's more pages of the flip book that the molecules have to go through in order to separate. And if you increase the number of theoretical plates, you're increasing the length of the flip book that the molecules have to go through. So this does increase retention time because it takes longer now to complete that flip book because you have to make more drawings on the pages in order for it to be a very smooth cartoon in the very end. The other problem here, not just time, but you're also going to have the chance of increasing what we call band broadening. And band broadening was something that we wanted to stay away from, right? This was something that we wanted to not have anything to do with because a band broaden takes your peak that should kind of look like that and it makes it into something that looks like this. And I don't want this to happen on my chromatogram, right? I want my peaks to come off and basically go back down to baseline in a very brief, short amount of time. And the longer it takes for the molecule to go through, the longer, or statistically speaking, the more chances of my molecules not coming out at one time, and instead I get this big fat blobby peak that comes off, and I'm really uncertain what's underneath the blobby peak, because there could be actually other components coming off with it, and that component is so fat and so wide that it's not going to show me what maybe else is present as the chromatograph is getting recorded. So this is not desirable here. This band broadening is something that's always a problem in the chromatography world, and I need to stay away from this if I can. So that's why we've listed the column length last as kind of your last resort to improve resolution, even though we know it will probably increase your resolution and make things separate enough. Well, we still run these chances of getting these fat blobby peaks that are hiding other things that might be coming off at about the same time now because of the interactions with the stationary phase. So one of the other ways that we can maximize resolution then is to decrease the height of the stationary phase. So, or the theoretical plate. So decrease HETP, and it reduces the size of the stationary phase particle. If I do that, the marbles become smaller, the pages become thinner, the separation becomes a little bit better, and that's something else that I could maybe choose as far as the theoretical plate world goes, and getting a better separation and a better resolution in the chromatography world. So we've talked about changing the mobile phase, we've talked about changing the stationary phase, we've talked about changing the flow rate, and the last one was changing the column length. But when you do that, you need to understand that changing the column length can cause more problems. And sometimes those problems, like they're listed here, are going to be big, major ones. It will make your peaks really, really fat, and you don't want that to happen. So you've got to be creative, and you've got to kind of fix that scenario if it does happen on you eventually. All right, so let's do an example problem here, and we'll quickly do a peak with a retention time of 407 seconds, has a width at the base of 13 seconds, a neighbor peak elutes at 424 seconds with a base width of 16 seconds. What is the resolution? Okay, this is how complicated these problems are going to be. No more complicated than this. It's just I got to make sure they're all the same unit first, and they are. Second here, the base is in seconds, the second one is in seconds, and the second base is in seconds as well. So resolution is equal to 2 times the retention times that are separated from each other or subtracted. So 424 minus 407, and then we're going to divide that by the width of the two bases. So this one's at 13 and that one's at 16. So 13 and 16. All right. So then I'm going to bring up a calculator, and I'll bring up the computer calculator for you. That way you can follow me as I do it. And we're going to type in 424, and we're going to subtract that from 407. And that gives me 17. And then we're going to multiply by 2, because I want to take the order of operations and I want to be really careful with it. And I'm just going to do it in step-by-step pieces. So 34 divided by, and then on the bottom, we're going to have 13 plus 16, and we get 29. So here on the bottom, I'm going to get 29. So to calculate resolution, I then take those two numbers and I divide them. So 34 divided by 29 gives me 1.17. 1.17 as my resolution value. Now, are these peaks separated? And you should give me the answer of no. And the reason is because 1.5 is the magic cutoff number. So if it's below 1.5, they are not resolute, which means they are too close with each other. And if I draw this chromatogram, just to kind of give you an idea, we get our first peak coming off at 407, and that's going to be here. And then the next peak is going to come off at 424. But look, this 407 second peak has a width of 13 seconds. So if I add 13 onto this, that's 420. So it comes down to baseline, but then it goes right back up, and then I get another peak that comes off. So the issue here is that they're close, but we need a better separation to feel better about the values in the chromatogram that I'll start reporting. So these two peaks are too close together. They are really close to 1.5, but they need a little bit of extra oomph in order to get them to separate from each other. So I changed the flow rate maybe, I changed the mobile phase, I changed the stationary phase, and then if all else fails, I changed the length of the column to see what I can get as a result of the separation as it goes through. So bottom line, the reason that we worry about resolution every single time is because we are going to be very focused on the areas under the curve, right? These peaks that show up on my chromatogram, those peaks are very important. And that's because I will be using areas in these calibration curves and in these calculations that I will begin to do. And if they are not separated from each other, then that means that the areas will conflict with each other. And now all of a sudden, I'm using numbers and values that I'm really not certain go along with that peak. So it's very, very important for us to achieve very good areas in the very end. And the only way that we can do that is if we have very good peaks that are side by side in order to do it with. So time is money and money is time. And you don't want to waste my time, and I do not want to waste yours. So for that reason, always keep that in mind. We don't want chromatograms that take an hour and a half to process per sample. If we can choose a different mobile phase, a different stationary phase, a different column, a different flow rate, in order to minimize the time needed for the chromatogram and still get good resolution, that is my job as a chromatographer. So in the next video, we'll pick up from here, and we'll talk more about time and flow rate.